Hello students, this is Dr. Ben. I'd like to take a few minutes to work through a problem out of Chapter 8 that has to do with the concept of rotational equilibrium. So here we have a model of a trap door that's over some kind of an opening in the ground that's being held open by a rope. And we're given a lot of information about the situation, and we're also told that the rope makes a right angle with the trap door. And what we want to do in this problem is to figure out what is the tension that is in the rope that is holding this trap door open. So let's go ahead and draw a force diagram. So the trap door itself has weight, and that points vertically downwards, and the trap door is pulled on by the rope, and so there's a tension in that rope. And there are also reaction forces that occur at the pivot, but we're going to neglect those for the moment, and actually for the whole problem, because they have no lever arm, and so therefore they don't cause any torque about the pivot point. So it's only the tension and the weight are the two forces that actually cause torques. So if the trap door is in static equilibrium, then we want to set the net torque that acts on the trap door equal to 0. And there are going to be two terms because there are two forces that act on the trap door that do not have 0 lever arm, and that's going to be the tension and the weight. And for each of the forces, we calculate the torque that's produced by that force by using the equation, the force times the distance times the sine of the angle that's between the lever arm, between that line of action and the force. Alright, so for our particular problem, then our equilibrium condition is going to give us two terms on the left-hand side. The torque due to the tension plus the torque due to the weight will be equal to 0. Alright, so the torque due to the tension will be equal to the value of the tension multiplied by the distance that force is from the axis of rotation that we're going to call L, the length of the trap door, and then times the sine of 90 degrees. And we see that if that was the only force that was acting on the trap door, it would cause a counterclockwise rotation, and so that term is going to be positive using our sign convention. And then the torque due to the weight is going to be negative because it would make the trap door rotate clockwise. So the torque due to the weight would be equal to the weight times the distance, which is now L over 2, because we pretend that the mass of the trap door is concentrated at its center of mass. And now we have to multiply by the sine of the angle between the trap door, and the weight. So if the angle that the trap door makes with the horizontal is equal to 65 degrees, then that means that this little angle up here is 25 degrees, and then the other angle that we want to find would be 180 minus that, so that would be 155 degrees. So I can actually go ahead and solve this expression for the value of the tension. So T times L times 1 on the left-hand side equals mg L over 2 times the sine of 155 degrees. Therefore, the tension equals mgL over 2L sine of 155 degrees. The L's cancel out, so I get mg over 2 times the sine of 155 degrees. So if we plug that into our calculator, go back and find the numbers that we need. The mass is 16.8 times 9.8 divided by 2 times 1.65 times 135 sine, and that equals 96 T equals 96 newtons. The tension is a force, and it should be measured in newtons. All right, so we found the value of the tension to be a size that balanced the torque that was provided by the weight. And we set up an equilibrium situation where we ensured that we had rotational equilibrium because the net torque was equal to 0.